Hello my dear wonderful genius students, I'm back again with a new video. This is lecture number 2 on complex analysis and it is the continuation of the last video. Today I'm going to teach you various representations of complex numbers. Students, we can represent a complex number in 3 different ways. First one is Cartesian form, second one is polar form, and the third one is exponential form. Let me explain you one by one. We can represent a complex number in Cartesian form in this way. Z is equal to x plus iota y, where iota is equal to root over minus 1. To get the polar form from the Cartesian form, we have to know the relationship between polar and Cartesian coordinates. I am assuming that you have very good command on polar as well as Cartesian coordinate system. The relationship between Cartesian and polar coordinates are as follows. X equal to r cos theta and y equal to r sin theta. Here r is the direct distance between origin and the point P, and theta is the angle made by the x-axis with r vector in anti-clockwise direction. So after substituting the values of x and y, here we will get the polar form of the complex number z as follows. Z is equal to r into cos theta plus iota sin theta. Again, to get the exponential form from the polar form, we have to know Euler's formula. According to Euler's formula, e to the power iota theta equal to cos theta plus iota sin theta. If you substitute this value here, we will get the exponential form of the complex number z as follows. Z is equal to r into e to the power iota theta. Here r equal to root over x square plus y square, and theta is known as the argument of the complex number z. This argument of the complex number z can be written as twice m pi plus principal argument of the complex number z. Here m can take these values 0, plus minus 1, plus minus 2, plus minus 3, dot dot dot. And one important thing is that this principal argument of the complex number z can take values in between minus pi to plus pi. Next, let me explain different topic, that is graphical representation of complex numbers. Students, we can represent a complex number graphically on eigenplane. In case of eigenplane, this horizontal axis represents the real axis and this vertical axis represents the imaginary axis. Suppose we have 4 complex numbers and we are going to represent these complex numbers graphically on eigenplane. For this complex number, along x-axis we have to move 3 units, and along y-axis, that means along imaginary axis, we have to move 3 units. So therefore, this complex number will lie at the first quadrant of the eigenplane. This one, first complex number. In case of second complex number, we have to move 3 units along negative real axis, and along positive imaginary axis we have to move 3 units. So therefore, the second complex number will lie at the second quadrant of this eigenplane Z2. In case of third complex number, we have to move 3 units along negative real axis, and we have to move 3 units along negative imaginary axis. So therefore, this third complex number will lie at third quadrant of the eigenplane Z3. Again, in case of fourth complex number, along real axis we have to move positive 3 units, and along imaginary axis we have to move 3 units in downward direction. So therefore, the fourth complex number will be located at the fourth quadrant of this eigenplane Z4. Now the next topic that I am going to discuss is how to find out the argument of a complex number z equal to x plus iota y. For finding the argument of a complex number z, we have to follow two steps. In the first step, we have to calculate the principal argument of the complex number z. After finding principal argument of the complex number z, we can find out the argument of the complex number z by using this relation. So first, let us understand how to calculate the principal argument of the complex number z. The given complex number is z equal to x plus iota y. So first we have to calculate this quantity, alpha equal to tan inverse modulus of y by x. After finding alpha, we have to check in which quadrant our given complex number is located. If the given complex number is located at the first quadrant of the eigenplane, then principal argument of the complex number z is given by alpha. If the given complex number is located at the second quadrant of the eigenplane, then the value of principal argument of the complex number z is given by pi minus alpha. Again, if the given complex number is located at the third quadrant of the eigenplane, then principal argument of the complex number z is given by alpha minus pi. And last, if the given complex number is located at the fourth quadrant of the eigenplane, then principal argument of the complex number is given by minus alpha. So after finding principal argument of the complex number z, we can find out the argument of the complex number z by using this relation, which is equal to argument of the complex number z is equal to twice m pi plus principal argument of the complex number z. Here m can take these values 0, plus minus 1, plus minus 2, plus minus 3, etc. Now let us do one problem. Write down the following complex numbers in exponential form. Exponential form basically means z equal to r into e to the power iota theta. Here I have given total 5 questions. Out of 5 questions, I will solve question number 3. I recommend all of you, please try to solve question number 1, 2, 4 and 5 by yourselves. Now let us do. Given the complex number is z equal to minus 1 minus iota. So first we have to calculate alpha. Here alpha equal to tan inverse modulus of y by x. Here value of y is minus 1 and value of x is minus 1. If we take the modulus, then we will get tan inverse of 1. We know that tan inverse of 1 is pi by 4. So after finding alpha, we have to check in which quadrant our complex number is located. So this complex number is located at the third quadrant of the eigenplane. So this complex number, the complex number z equal to minus 1 minus iota is located at third quadrant of eigenplane. So therefore principal argument of the complex number z is given by alpha minus pi. In our case, the value of alpha is pi by 4. So therefore the value of principal argument is given by minus 3 pi by 4. So after finding principal argument, we can calculate the argument of the complex number z. So therefore the argument of the complex number z is equal to twice m pi plus principal argument. So in our case, the value of principal argument is given by 3 pi by 4. Next, we have to calculate the value of r. So here r is given by root over x square plus y square. Here x equal to -1 and y equal to -1. -1 whole square plus -1 whole square, which is equal to root over 2. So therefore, the exponential form of this complex number is given by, therefore the exponential form of the complex number z equal to -1 minus iota is given by z equal to r. R means root over 2 into e to the power iota theta. Iota, the value of theta is twice m pi minus 3 pi by 4. 3 pi by 4. Let us take one special case where m equal to 0. So for m equal to 0, the exponential form of this complex number z will be equal to root over 2 into e to the power minus iota 3 pi by 4. Okay? Now the next topic that I am going to discuss is properties of modulus of a complex number z. Here I want to mention one point is that I am not going to derive all these relations because these are very fundamental relations, and I am recommending all of you please try to derive all these relations. First, just I want to mention, or I want to revise what is the meaning of modulus of a complex number z. We know that if z equal to x plus iota y, then modulus of the complex number z is given by root over x square plus y square. Next, let us discuss these properties. If z1 and z2 are two complex numbers, then modulus of z1 plus z2 is always less than or equal to modulus of z1 plus modulus of z2. Second property, modulus of z1 minus z2 is always greater than or equal to modulus of z1 minus modulus of z2. Number 3, modulus of z1 into z2 is equal to modulus of z1 into modulus of z2. Number 4, modulus of z1 divided by z2 is equal to modulus of z1 divided by modulus of z2. Next, properties of argument of complex number z. First one is argument of z1 into z2 is equal to argument of z1 plus argument of z2. Second property, argument of z1 divided by z2 is equal to argument of z1 minus argument of z2. From these relations, we can say that this argument always follow the logarithmic rule. So this is all about today's video, and I hope that you have learned a lot from this video.